In the last video, we discussed how IPv4 headers work together to deliver packets across the internet. We also went over how the identification, flags, and fragment offset headers are used to handle packet fragmentation. To further solidify this concept in this video, I'm going to go over how MTU and fragmentation works in practice on a computer network. Before we talk about fragmentation, first we need to understand MTU, which stands for Maximum Transmission Unit, and this is the largest size packet that a network will accept. Typically, this is a value of 1518 bytes, 1500 being the payload and 18 being the Ethernet header. However, MTU can vary from network to network. You as a network administrator may set an MTU of 1000 and another administrator may set theirs to be 1300. So the MTU is very much dependent upon the network as it's been configured by the administrator. However, in practice for something such as the global internet, 1500 will be the common MTU that you'll see in reference to the payload that's supported. So the sender only knows the MTU of the local network, and when data cannot fit on the wire due to an MTU limitation, the packet then gets fragmented. And when that fragmentation occurs, the receiving device needs to know a couple of things. First, it needs to know that the packet received is a fragment of one big packet. Next, it needs to know the order of the fragments. You have to remember that every packet on a network is routed individually and it may arrive out of order. Just because the sending device puts the packet on the wire in a certain order does not mean the receiving device will get the packets in that same order. And lastly, the receiving device needs to know that the packets received are not duplicates. So let's take a look at how all of this works in practice. Let's say we are on computer here. We'll say we are PC1, and we're going to send some data over to server 1. So the data that we send, it's going to have the maximum transmission unit of 1500 as being sent out from the computer. And let's say our computer is connecting to router 1, and router 1 needs to make a forwarding decision. How do I reach server 1? So let's say it reaches server 1 out this link right here. However, this link only has an MTU of 500. So it will not accept the 1500 MTU that the computer has sent to the router. At this point, this is where the packet would be fragmented. So we would cut this packet up into 3 individual pieces. 500, 500, and 500, giving us the original 1500. Now, how does the receiver know that this is not a normal packet? How does it know that this is not a duplicate packet? How does it know it's a fragment? Well, each fragment is given the same ID value that tells the recipient that these are fragments of a larger packet. So each packet will have its individual header with an ID value. And that ID value is typically randomized for every packet that you put on the wire, but in the case of a fragment, it's always going to be the same. So if we say that the ID value is 25, that is going to be the ID value in that IPv4 header for every packet that's sent on the wire. So not only does the host use the identification field to identify whether or not the packet is a normal packet or a fragmented packet, there's also a flag field in which there's a more fragments bit that gets set. So whenever a packet gets broken up from, say, 1500 to 500 apiece, like in this example, the first 2 packets, in this case we have 3, but the first 2 packets are going to have a more fragments bit set. And this is going to be the case for however many fragments there are minus 1. So if you have 8 fragments, the first 7 are going to have this bit set. And this is to let the receiving device know that this is a fragment of a larger packet and that there's more fragments to come. So you may be thinking, okay, this works for packets that get sent in order. However, what about the cases where the packets are sent out of order? What if the computer sends 3 packets in a row and for some reason or another, the packets arrive at the destination in a different order, not in the order that the host sent those packets in? And that's where the fragment offset fields come into place. So let's clear this off real quick and take a look at that. The fragment offset bit is an indication of how far away from the front of the packet the fragment is located in bytes. So if we take a look at the original example that we had here, where we had our packet that was 1500 bytes in size, and we chopped it up into 3 pieces. And let's say that we sent this out in order 1, 2, 3. However, the receiving device did not receive those packets in that order. Maybe it got the first packet last. And we'll do something like this. The second was received first, and the last packet was received second. So this is the sending device, and this is the receiving device. Now, there's a few things here that are going to be the same across these packets. First, if we go back to the identification field, we said before that was 25. This value is going to be set across all 3 packets. Additionally, when we are looking at the more fragments bit, that's going to be set on 2 of these packets. So we said before that the more fragments bit gets set on all the packets except for the last one that gets sent in the fragmented chain. So if we send 3 packets in order, the first 2 will have the more fragments bit set, so the receiving device knows that the packets received are a fragment of a bigger packet. However, the last one will not have that field. And then next we have the fragment offset. So this value is 0 for the first packet that gets sent. And let's just say that the next fragment is 501 bytes away. So the fragment offset for packet number 2 will be 501. And we'll say that for the last one, it's 1001. So at this point, the receiver knows that the packet is a fragment because the more fragments bit is set. It knows that it's not the first packet, otherwise the fragment offset would be 0. And it's not the last packet, otherwise the more fragments bit would not be set at all. So again, to reiterate, from a receiving device perspective, when we take a look at the way that these packets were received, we have this first packet here. We know that this is a fragment because the more fragments bit is set. We know that it is not the first fragment because the fragment offset has a value that is not 0. So we know that this is not the first packet. However, we do know that it's a fragment. So now we get the second one. And we do the same logic. We know that it's part of a fragment because the ID numbers here match. And we also know that it's not the beginning of this fragmented chain because the fragmented offset is set to 1001 in this case. It's not 0. And then when we get the third packet here, we can see that, again, it has the same ID value. It has a more fragments bit set. And most importantly, the fragment offset is set to 0. So we know that this is the first packet that was sent in the fragmented chain. So when we take this all into account and we look at the fragment offset values, you can effectively chain them together. You can see where they should be placed in order to recombine the packet in the proper order. We know that we need to put fragment offset 0 to be the first, followed by fragment offset 501, followed by fragment offset 1001. If you have any questions about what was covered, please leave a comment below. And if you enjoy these tutorials and want to support my work, please like this video and share it with others. Be sure to subscribe to stay updated on my latest content, and thank you all for watching.